So as I was saying, so this sequence gets the despreaded sequence is generated using the spreading sequence only. So this spreading sequence only, the despreaded sequence is generated, and then they are accumulated, and based on the threshold decision making, the final data is decided. Now, in this sequence, we already know there is something called as noise. So the received signal, you are transmitting the signal. Along with that, it is getting corrupted by noise NT. So that is AWGN noise corruption. So that we all know. But apart from that, there is another phenomena that is happening here, and that is interference. So in interference, because you are in this spread spectrum, you are allowing multiple users. So there will always be some interference among the users, and one user's data might interfere into another. So this interference is another impairment that we have to take care of. So we have to do first an analysis of this interference, then we have to figure out ways to mitigate this interference in spread spectrum. So the interference is basically taken as a like a of the form of a sinusoid. So the interference is also taken as a form of sinusoid, because this other signals are also transmitted. The interfering signals, they are basically other user signals. So since this user is getting transmitted in sinusoidal form, the other users are also expected to be transmitted in sinusoidal form. So the spread spectrum interference is also assumed to be of the interference of this sinusoidal form. So here specifically we are taking a single tone, I root 2I cos 2 pi f1 t plus theta 1. So here I f1 and theta 1 are the average power, frequency and phase angle of the interference signal. Okay, so this is the this tone, this is the interfering tone f1. So all the accumulated interference from various sources are assumed to be accumulated into a single tone, and that is the interfering tone f1. So this f1 is assumed to be close enough to the desired frequency fc. So yeah. Mhm. Now we have to do further analysis of this tone. So yeah, if f1 plus fc, now since f1 and fc are assumed to be very close, so f1 plus fc is assumed to be much greater than f1 minus fc, because f1 and fc are pretty close, so their difference is negligible. So that a term involving f1 plus fc is negligible. Why f1 plus fc is negligible? Because here you can see that this this is basically a this sinusoidal term. So f1 plus fc is, if f1 plus fc is larger than f1 minus fc, so minus fc is near to cos 0, right? So if f1 minus fc is very near to cos 0, cos 0 is the maximum value, so we can say that f1 minus fc term will dominate, because this is cos, so it is very near to 1. So f1 minus fc we are writing as ft. So this yeah, now we finally to get the interference power, we will multiply this interfering tone. We will assume that this is like this it, this it is the interference signal. To get the interfering power, we will multiply the interference signal with the interfering tone. So here cos 2 pi fct is the carrier tone, and this interference is it. So finally, if you integrate and do some manipulation, your final interference power will come as this. Okay, so this will be a function of fd, where fd is f1 minus fc, the difference between the interfering tone and the desired frequency. Acha. And yeah, um, and for a rectangular waveform, the evaluation of the integral will yield this kind of a structure, where tc, where sinc fdtc into cos 2 pi fdt plus theta 2, where theta 2 is theta 1 plus pi fdtc. So this is the where tc is like the coherence time. So here chip duration, sorry, chip coherence time or chip duration tc. So substituting 133 into this, we will finally get the variance of this tone, the variance of this power to be this ITC square sinc square into G plus this cos residual. So G is equal to TS by TC, where TS represents the symbol duration. So it is evaluated like this, and then you do further simplification and you get the expression of the variance. Okay, so this is basically the general interference and its variance. So finally, with that variance, you can also do a noise signal derivation, and the noise signal will come as this. So of the interference, so there is a noise, normal noise n naught, plus this term is your interference term. So this term is basically adding on to the noise. So n naught e phi becomes a equivalent two-sided PSD of the interference plus noise. So n naught is the noise power spectral density, and along with that you get a additional interference term like this. For sinusoidal, this one was for rectangular, this is for rectangular, and for sinusoidal you get something similar like this. Mm, yeah, so these are your derivations. Now we will go to Gaussian interference. So again we take the same system, synchronization design, devices chip match synchronization device synchronizes the received signal, then we have a match filter, then sampler to get the final received samples, and then we despread that using the spreading sequence generator. We accumulate that and make a decision based on the threshold. Now we get another kind of interference. First one was tonal interference. So the first problem was tonal interference. Now the second one is Gaussian interference. Here IT will be just like NT is a Gaussian process, IT will be another Gaussian process. So we are approximating IT and NT both to be Gaussian. So the interference is modeled as a zero mean stationary Gaussian process. So these are various models of the interference, and based on the actual real data we have to see which model fits our interference perfectly. Okay, perfectly or like in a better way. So in a better way. So if IT is modeled as the Gaussian interference, so IT is the Gaussian interference, and yeah. Mhm. And then you do uh, this and phi t is the chip waveform. What is the chip waveform? Chip waveform is basically the spread spectrum. You are doing the spread spectrum, so the equivalent waveform of the spread spectrum is the chip waveform, and you multiply that and the cos 2 pi fct, so to get the Gaussian interference power and the expectation of ji square. So this thing itself is ji, and if you take the expectation of ji square, you will get something like after trigonometric expansion and dropping of some integrals, finally a simplified process. Now these exact you can find in these exact derivations you can find in the lecture or in the textbook. I will, since this is primarily a problem solving session, I will not go through the exact steps of the derivation. I will just give you a brief overview of what is what. So here this is the interference expression. So here we have the cos term, and we have also, since there are two integrals, both are time, so basically we have to take the autocorrelation of the t1 and t2. Basically correlation, the cross correlation between the signal at t1 and the signal at t2, that is basically the autocorrelation. The autocorrelation of the cross correlation of the same signal at two different instances is known as the autocorrelation. So basically the correlation between the signal at t1 and the same signal at t2. So of which signal? It, the interference signal. Here we are not dealing with the signal of the noise. We are only dealing with the interference signal it. Since Eji square does not depend on the index I, so we can say variance of V1 equal to this, then this. Yeah. So again, we can take the 1 minute. Hello. हाँ बोल. हाँ. একই ব্যাপার তো, একই ব্যাপার। মামার লরিও তোকে 100% ইনভেস্ট করে। মামার লরি যা প্রাইস লিখে দেবে ওরা ইনভেস্ট করে দেবে। মামার লরি যা প্রাইস লিখে দেবে ওরা ইনভেস্ট করে দেবে। মামার লরিকে ওরা কোয়েশ্চেন করে না। তোর ইয়েটা ও আরামসে করে দিচ্ছে, মানে তোর হেডেক নয়, আইআরসিটিসিটা তোর হেডেক। না 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 না, দুটোই ইকুইভ্যালেন্ট, বাট তো আইআরসিটিসি হলে তোর নিজে হেডেক নিতে হবে। হ্যাঁ, বিল আর টিকিট, হ্যাঁ হ্যাঁ, ইনভয়েস আর টিকিট সেম। মানে ওটা মানে আইআরসিটিসির চেয়ে 8,000 বেশিও নিলে তোকে 8,000 দেবে না এমন না। বাবার লরি যা দিচ্ছে কোট করছে সেটাই ওরা দিয়ে দেবে। হুম, হুম, okay, হ্যাঁ। Hello. Yeah. So where were we? Sorry for the interruption. So this finally we get the variance of the interference like this Eji square, which is a double integral. So finally summing of the expectation of ji square will give you the variance. Okay, and the variance turns out to be G Eji square, where G is the symbol duration, G is Ts by Tc, basically the symbol duration by the chip duration, processing gain as we say it. So processing gain into Eji square. So finally, yeah. So evaluating one of the resulting integrals and substituting the result will give you this kind of a thing, and where lambda is the triangular pulse. Okay, and yeah, since rj tau, now you have a convolution, sorry, an autocorrelation function and a autocorrelation of the Gaussian and the triangular function. Now they are saying the autocorrelation of Gaussian and the triangular function, the product of them is a even function. Why? Because at a triangular is also an even function, and autocorrelation of a Gaussian is also even, so it is a even function. So the final result is um, then the convolution theorem and the known Fourier transform of lambda t will yield final result, and they are pushing the limits. The limits in the equation can be extended to plus minus infinity because the integrand is truncated. Means basically that since this is a triangular pulse, so beyond the tc to minus tc it is 0. So tc to minus tc, whatever the value is, plus infinity to minus infinity, result will be same. Basically from tc to infinity and from minus tc to minus infinity, the integrand is 0. So extending the limit up to there does not change the material value of the integration. So you can just change to minus infinity to minus infinity, and you take the Fourier transform. So basically the Fourier transform will give, the autocorrelation Fourier transform gives power spectral density, and the triangular Fourier transform will give you this thing. So yeah, so finally the variance in the frequency domain is this. Okay. Hmm. So since IT is a zero mean Gaussian process, the JI, the interference terms, are zero mean and jointly Gaussian. Uh, so the variance of V1 does not depend on Pi. Vi1 without conditioning is a zero mean Gaussian random variable. So it does not depend on the power. So it is always centered at 0. This variance of V1, and the independence of thermal noise and interference imply that V equal to V1 plus V2 is also, so interference plus noise, because interference is Gaussian, noise is Gaussian, and they are independent. So the addition of interference and Gaussian noise will also give you a zero mean Gaussian random variable. Hmm. So again there is a plot for the binary signal to interference ratio versus probability of symbol error. You have to plot this kind of plots in the MATLAB assignments. Okay, now we will be doing some problems. So I will give you some time. Okay, first of all, please ignore this. This is a mistake, the first line. So start reading from the bold face. Ignore this. This has been repeated. Yeah. So start reading from a direct sequence. A direct sequence spread spectrum BPSK system has a data rate RB equal to 50 kbps and a chip rate of 5 Mbps. So 10 if you have a 50 kbps data is coming, you have to make it 5 Mbps along with the chips. So chip plus data should be transmitted in 5 Mbps. The received signal to noise ratio is EB by N not equal to 60. A broadband jammer produces J by S equal to 15 dB. So JYS means jamming power by signal power. So jamming power by signal power is 15 dB at the receiver input. So we have to compute the processing gain. We have to compute the effective J by S after desplitting, and we have to determine whether reliable communication is possible if BPSK requires EB by N not greater than 5 dB. So first we have to compute the processing gain, and we have to compute the effective JYS after desplitting. I think these two can be attempted by you. So part C I will show rather. Part A and B, please do. I will give you what, it's 26. I will check at 30. Please try at your end. If you have the answer, please reply in the chat box or open the mic and tell the answer. Yeah, so let's go to the solution. So the first is processing gain. The processing gain is very simple. It's just the chip rate by the data rate. So yeah, Mr. Suresh Patel, please go ahead. Please go ahead. Do you have any query?
Process gain is 20 dB.
Process gain is 20 dB. So let's check. Yes, you are absolutely correct. Processing gain is 20 dB. So it is the chip rate by the data rate. So next is effective jamming power after despreading. So yeah, so after despreading, the effective jamming power, it will be reduced to it was 15 dB previously, it will be reduced by 20 dB. So minus G. So the final jamming to spread jamming power, effective jamming power, so jamming power by signal power will be minus 5 dB, which is 0.316. So thus the jammer power is 0.316 times the signal power. Now and the system EB by N naught is 6 dB, and EB, the required threshold is EB by N naught is 5 dB. So since the jamming degradation is only 0.316 and there is a margin of 1 dB, so we can say that the communication will remain reliable. So because the jamming power is minus 5 dB, so it is below the margin. So it is originally was 6 dB and the threshold for communication is 5 dB. So you have 1 dB margin. So and this jamming is taking, means this jamming is having only this much effect, not full effect. So 1 dB is sufficient to, means this 1 dB margin is sufficient and the communication remains small, because reliable, because the jamming degradation is small, minus 5 only. But if the jamming degradation was more than 1 dB, say 2 dB, instead of minus 5 it is plus 2 or plus 3, then your communication wouldn't have been reliable. Okay, because it is minus 5, it is less than 1 dB, so we can still communicate. Okay, and next is a DS3 BPSK system operates with EB by N not equal to 7 dB and processing gain is 25 dB. the jammer power equals signal power before spreading, despreading. Compute the resulting BA. So DS3 BPSK is there. The EB by N naught is 7 dB and the processing gain is 25 dB. The jammer power equals the signal power. So J by S. The J by S, 1 minute. Just take out the pen, writing pen. Yeah. So here you can see the jammer power equals signal power before despreading. So J by S before, J by S naught is 1 in linear, or in decibel it is 0 dB, right? So that is what is shown here. J by S is 0 dB. Next, the processing gain is 25 dB. So what will be the J by S after? After despreading, what will be the J by S? It will be 0 minus 25. So it will be minus 25 dB. So the J by S after is minus 25 dB. So the jamming contribution is negligible. So minus 25 dB is basically 0. So it is negligible. So your BPSK EB by N naught remains unaffected. So it is EB by N naught is what was previously 7 dB, that only will remain preserved. But if this J by S after despreading was maybe 4 dB, then your effective EB by N naught would have been lesser. Okay. So since the jamming contribution is negligible, EB by N naught is 7 dB. 7 dB roughly translates to 5 in linear terms. Now PB is equal to Q of root under 2 into 5. So the bit error probability is Q function of the EB by N naught. So it is Q of root 10. So Q of root 10, of course, you have to consult a table. You cannot find on your own. And the Q of root 10 is PB equal to 7.5 into 10 power minus 4. So the bit BER is 7.5 into 10 to the power minus 4. Okay. Next one is frequency hopping spread spectra, collision probability. So in an FHSS system has 100 hopping channels and 10 independent users. Each user selects hop frequency uniformly at random. So there is the hop frequency is selected using a uniform distribution. Find the probability that a given user experiences at least one collision in a hop interval. So there are 100 hopping channel and 10 independent users. So the probability that a given user experiences at least one collision. So at least one collision means it is the complement of no collision, right? So the easier way is to find it is the complement of no collision. So what is the probability of no collision? So the probability of no collision is that all of this 100 that is assigned their own channels. So the probability of no wait, I think this is wrong. No. Ha. Yeah. So what is the probability? Say you start with one user. Okay, user A. This is your user with which you are working. Now, what is the probability that it is assigned the same channel as user B, which means it will be colliding. So user A has taken a channel and there are 100 channels including the one user. Say user A has taken channel 3. Now there are 100 channels. But for user A and user B collision to happen, what is the channel, what is the probability? It has to choose the channel 3. So it has to choose, it can only choose one channel out of 100 channels. So the probability that user A and user B will have the same channel is 1 by 100. So what is the probability that they will not have the same channel? That is 1 minus 1 by 100. That means user A is avoiding collision with user B. Similarly, the probability that the channel allocation of user C, now we come to user C, that the channel allocation of user C is independent of channel allocation of user B. What channel user C gets allocated is independent of what B gets allocated. So again, independent means their probabilities will be multiplied. So this is again 1 minus 1 by 100. Understood? Like this, since user A's channel we have already assigned, we will have 9 other users. So 9 other users will have 1 minus 1 by 100 like this. So 1 minus 1 by 100 is 0.99. So the final answer is 0.99 to the power 9. So this is the probability 0.913. Now this is the probability of what? This is the probability of collision avoidance. Right? We are finding the probability of avoiding collision. Now, what is the probability of at least one collision? At least one collision is just the complement of avoiding collision, of no collision. So at least one collision will be just the complement of no collision. So it is 1 minus 0.913. So it is 0.087 or 8.7%. So there is roughly a 9% chance that there will be a collision if 10 users are hopping between 100 channels. Is this question clear? Okay, I hope it is clear. Next is tone jamming effect on coherent BPSK. A tone jammer of amplitude A at carrier frequency is added. Derive the decision statistic after coherent detection. A BPSK system transmits this where BT is equal to plus minus 1. So this is your standard BPSK system, right? Now a tone jammer of amplitude A at the carrier frequency is added. So okay, this line again has been repeated. So please ignore this line. So the question starts from a BPSK system transmits. This part is again repeated. A BPSK system transmits this thing where BT equal to plus minus 1. So root 2p BT cos 2 pi of ct. Now a tone jammer of amplitude A at the carrier frequency is added. So derive the decision statistics after coherent detection. So there will be a jamming signal or interference signal which will get added to the signal, main signal, and it will have an amplitude A. This one has an amplitude of root 2p bt, and that will have an amplitude of A. And this JT, the jamming signal JT, will have an amplitude A, and it will have the same frequency as the carrier frequency. So the jammer has perfectly detected the carrier frequency and it is adding at that carrier frequency. So the final received signal will be the sum of these two. So the final received signal will be ST plus JT, means it will be A plus root 2 PBT, and the tone part will be same because the jamming is happening at the exact same tone as the signal. So this is your RT. Now to get coherent detection, what happens at coherent detection? Your RT comes, you multiply it with the at a local oscillator output which generates the exact same tone that has been used in the transmitter. So this is the work of a local oscillator, and then you integrate or you basically pass through a low pass filter. Same thing. In time domain you say you integrate, in frequency domain you say you pass through a low pass filter, and you get the result of coherent detection. So basically you have to multiply this cos with cos 2 pi fct to get the result. So let's take a fresh page and do that instead of just following the work. So in fact, it would be better if you can just do the integration instead of me doing it. Wait, I will just write down the integration properly. Now this st is let's write it in a better way, uh, or you can write it as plus minus root 2 cos 2 pi ct because bt is plus minus 1, so you can just write plus minus root 2. And what is the jamming signal jt? It is amplitude a and same tone. So the received signal rt is this st and the jam signal jt. Okay, so this is a plus minus root 2p cos 2 pi fct. So coherent detection means coherent detection output is integration of rt times cos 2 pi fct dt. So it is integration of a plus minus root 2p so you take half as you do, so a plus minus root 2p 1 plus cos 1 plus cos 2 into 2 pi fct dt. So this will become half a plus minus root 2p now this t will be integrated over 0 to tb, the bit duration. So this is 0 to tb and you get tb. And another term is there which is the cos 2 theta term, but we can ignore that term, we can put it to 0. So finally you will have TB by 2. So yeah, now the decision threshold, this thing decide 0 if a TB by 2, say minus root 2p, is less than 0, implies a implies yeah, a by 2 lesser than 2 root 2p by TB. This thing basically becomes your new decision. So you do 2 root 2p by 2 root 2p by TB, and you compare that with, not a by 2, sorry, a. So you compare that with a. If a is less than 2 root 2p by TB, you decide 0, else decide 1. So this becomes your decision threshold. In an ideal case, you will have a less than 0, a greater than 0, like that. But here the error floor changes. The a less than 0, a greater than 0 threshold. Now the threshold has changes to a less than 2 root 2p by TB, a greater than 2 root 2p by TB. So the error floor changes. DC bias shifting threshold changes. Okay, a jammer concentrates its power over fraction rho equal to 0.3 of spread bandwidth. Compare its effectiveness to full band jamming. So a broadband jammer will be focusing on the entire bandwidth. So the jamming power JT will be spread across the entire bandwidth, whereas here it will be spread across 30% of the bandwidth. So 0.3 W, partial band jamming. So the partial band jamming will of course be 1 by 0.3 or 3.33 times stronger. So I think this does not need further expansion. So basically, if there is a jammer here, the jammer transmits a fixed power, PT, or in this case JT. Now this JT, if you spread it across the entire bandwidth W, of course the effective PSD will be JT by W. It will be spread out. Whereas for partial band jamming, it will not be spread out. It will be more focused across the chosen band. So it is JT by 0.3 W. So the partial band jamming in jammer, so PSD, say PSD dash. So PSD dash is by PSD is 1 by 0.3. So 3.33. So PSD dash, that is partial band jammer, is 3.3 times stronger than total band jammer. So of course, whenever feasible, we should be focusing on a dedicated bandwidth of the jamming rather than jamming everything under the sky. Okay. Okay, do this. This is pretty easy. This question, spread bandwidth equal to 10 megahertz. Compute processing gain for data rates 10 kbps and 1 mbps. Do it and report the answer as soon as you can. Yes, please go ahead. Unmute.
Says Dell is 30 dB.
30 dB. And next. Next one is 10 dB.
10.
Yeah. So, so if you, what is the, so this is, I don't think requires any explanation further. But the main takeaway from this is, if you, uh, is there some kind of notification? Oh, okay. Yeah. Is there any other doubt, Mr. Suresh Patel?
No, sir.
Your hand is raised actually. Okay, I'm lowering it. Yeah. Okay, fine. So the calculation does not need any explanation, but what I need to say is that for 10 kbps data, you see that you have a higher processing gain. But if you want to, basically, processing gain, you have higher processing gain because you are spreading a very small data across a large bandwidth. So you are, of course, you will have very good processing gain. It will be more robust. But 1 Mbps means it's nearly there. 10 megahertz bandwidth, still not there, but it is nearly there, much closer to 10 than 10 kbps. So basically, it is now not spreading much. It is nearly using all the resources. So the processing gain is less, and it is less robust because your data is now not that spread across. The more you spread your data, that is more your spread bandwidth is relative to your so relative to your data rate, the better anti-jamming robustness you will have. So here you see that lower data rate has a processing gain of 30 dB. That means it can tolerate up to 30 decibels of jamming above the level, the signal level. So it can tolerate up to 30 dBs of jamming above signal, whereas a 1 Mbps signal can only tolerate 10 dBs of jamming above the signal level. Okay, now, okay, now this signal bandwidth is 1 megahertz, signal to noise is 10, and jamming is equal to signal. So compute the channel capacity. Basically Shannon's formula. Try it. This now is 1957. So at 8 o'clock, by 8 o'clock turn in the result. That is in 3 minutes. Try this. So any results? Mr. Suresh Patel, uh, Ms. Anu Sharma, any results? Okay. So see, jamming and noise. Jamming is basically another kind of interference, right? So jamming is SNR is decided by, means here SNR is decided by not only signal and noise. You have to write all the desired power. The capacity is decided by all the desired power divided by the all the undesired power. So the desired power, the power that you want the receiver to get, is what is in the numerator. So SNR, it can be SINR, it can be SJNR. In this case, it is SJNR. So signal to jamming plus noise ratio. In some cases, it might be SINR, signal to interference plus noise ratio. So whatever is desirable, like signal, is at top, and whatever is undesirable, like noise, interference, jamming, is at the bottom. So here there is no interference, only jamming. So it will the metric will be SJN, and the Shannon capacity is a general equation. The Shannon capacity will be C equal to C is capacity, B is bandwidth, B into log base 2 1 plus SJNR in this case. Okay, so let's take this to the yeah, to a better writing space. So the we have decided C is equal to B into log base 2 1 plus SJNR. Now S by N is 10. So N is S by 10. Further, it is given that J is equal to S, the jamming power equal to the signal power. So J equal to S. So SJNR is S by J plus N, or S by 10 plus S. So it is S by 11 by 10 S. That is 10 by 11. So SJNR is 10 by 11. So C is equal to B. B is given to be 1 megahertz. So 1 into log base 2. 1 plus 10 by 11. Megahertz means it will be Mbps. So it is log base 2 21 by 11 Mbps. So you just do log 21 minus log 11 in calculator. Yeah. So log 21 minus log 11 is log 21 minus log 11.28. Let me recheck. Yes, log 11. Yes, 0.28. So it will be 0.28 Mbps. That is the fundamental capacity of the channel. That is the maximum data rate you can get under these conditions, 0.28 Mbps or 280 kbps. So that is the absolute theoretical maximum data rate that you can get in this condition. Did I do the log calculation wrong? 10 by 11. Wait. 10 by 11. Oh, sorry. I have done a mistake, I think. No. 11, 21. Yeah, no, no. 21 by 11. This calculation is correct, right? 21 by 11. Yeah. Why isn't it matching? Log 21 minus log 11. Okay, this was, sorry, this was base 2. So this will be base 2. So you have to just divide by log base 2. So you will get 0.93. I did log base 10. So it will be log base 2. So in log base 2 it will be 0.93. 0.93 Mbps. Okay, that was a silly mistake. I did log base 10. In log base 2 it will be 0.93. So the correct answer is 0.93. User A, now we take another problem of interference. User A received power 1 watt. User B received power 0.01 watt. So determine processing gain of user B. I think processing gain is not written clearly. Power we should do. Yeah, processing gain is 20T. So processing gain of user B is 20T. So determine if user B survives the interference. How to do this? Processing gain of user B is 22. Just write down user B here. Okay. How to do this? Any idea? Wanna try? Take 2 minutes, 2-3 minutes, and try it on your end. Just J by S. We have to find the before and after of J by S. That is it. Here, jamming power is basically the interfering power. That is user A. So user A's power is basically the jamming power here. Try for 2 minutes.
Sir, basically the power ratio of A by B is the 100, means that there is a PG of 20 dB,
Yes.
and already is the gain is 20 dB. I think just B is survive. मतलब jammer power equal to
No, just
A
survive now. Basically, no, it will not survive. It needs some margin. There
is
is no margin. So yeah,
awesome.
with the J by S will be basically nothing after.
Nothing.
So
Yes.
so J by S before. So very good. So the J by S before was J by S before was
20 dB.
20 dB. So 10 log 1 by point 0.0 dB. So it
One
is
by
20
100.
dB. And then after the J by S will be 0 dB because 20 J by S
20
before
minus 20.
minus PG minus PG. So 20 minus 20, so 0 dB. So 20 minus 20 is 0 dB. 0 dB means there is no margin. So it is at system is at threshold. So it is high rate. It will probably not. It will need some margin. So you can say system is at threshold. It will need some margin. So it cannot communicate. It will need some margin to communicate. So because that margin will be your new EB by N naught, right? So you will have 0 EB by N naught right now. So next is the fast versus slow. Next problem is fast versus slow FHSS. So symbol duration is 1 millisecond and hop duration is 0.1 millisecond. So a symbol is lasting 1 millisecond, but the frequency is changing every 0.1 millisecond. So is the system fast or is it slow? What will be the answer? Is it fast or is it slow? It will be fast. It will be a. Can you answer? Just looking at the values only. You don't need any calculation. Yeah.
Fast. Or
Yes, fast. Because in one symbol duration only, the frequency is hopping 10 times. So the number of symbols. The number of hops in one symbol duration should not be more than one. So you are having multiple hops. So it is a fast FHSS. Or more simply put, wait, or more simply put, the symbol duration is greater than hop duration. So it is fast FHSS. Or hop duration is lesser than symbol duration. So it is fast FHSS. Huh. Okay, next. Processing gain is 30 dB. Required dB by N naught is 5 dB and operating margin is 2 dB. So find the minimum J by S required before despreading. So you need a EB by N naught of 5 dB and you also need after that a margin of 2 dB for maybe other unforeseen noises and fluctuations that you might have. You will need another 2 dB. So you need 7 dB. So find the minimum J by S 7 dB margin. So find the minimum J by S before despreading. Can you do that?
Twenty-three
23 dB. So
dB.
30. But the thing is, uh, must processing gain and margin. But the thing is, this communication EB by N naught. Yeah. Okay. So basically, the jamming must overcome the required EB by N naught is 5 dB. That is fine. But the jamming just has to overcome the operating margin and the processing gain. So the jamming needs to be 30 and it has to be basically what will be subtracted from it. 30 plus 2. I think the 5 dB should also be there. So yeah, it will not be 30 plus 2. It will be 30 plus 2 plus 5. So yeah, so required EB by N naught is 5 dB. This one is actually a bit wrong. So EB by N naught you need 5 dB. You need to jam that. You need to jam the margin and you need to jam the processing gain. So see, you are subtracting these, but the thing is the J by S after is equal to J by S before minus processing gain and minus all these margins. So the J by S after it just has to survive minimum. So the JYS after minimum should be what? 0, right? So here this one is wrong actually. So the JYS before, sorry, JYS after is JYS before. What was before? And what gets subtracted? The PG gets subtracted and all the margins. EBY and not get subtracted and the margin gets subtracted. So the before, now they are asking the before JYS, not the after JYS. The before JYS. And what is the JYS after? They are asking for the minimum. The minimum is when there will be 0 dB. So 0 is equal to JYS before. So let's JYS B minus 30 minus 2 minus 5. So JYS before will be 37 dB. In by 30, if you send a 37 dB jamming signal relative to signal power, 37 dB jamming power, you will entirely jam the system. Or sometimes in some definitions you might see that you know don't need to overcome the EB by N naught. You just have to overcome the margin and the jam processing gain. Then it might be 32. So I have to consult the definition here. I think. Wait 1 minute. Yeah, it does not need to overcome the EB by N naught. Basically, it just needs to overcome the processing gain and the margin. So it just by definition, it just needs to overcome the processing gain and the margin. So it is 30 plus 2, 32 dB, not 35 dB. This one will not be there. So it just needs to overcome the jamming, the processing gain and the margin. And sometimes this margin might not be given, so it just has to overcome the processing gain. The EB by N naught is independent of this process. Okay, so that concludes this part, problem solving part. Mhm. Now we will turn to the topic of matched filters. So we usually use matched filter in the receive signal for synchronized detection, right? So we use matched filter in the receiver for synchronized detection. So yeah, synchronized detection we use match filter. So similarly for like demodulation, we want to use jamming for despreading. So we want to use jamming for despreading. jamming, sorry, I mean to say match filter for despreading. So despreading short spreading sequence with match filter provide inherent code synchronization. The spreading waveform for a short sequence may be expressed as this thing, where the spreading waveform is this P1, and then it is repeating across time periods. Now, if the short spreading sequence has length n, then it can be expressed as, in the short spreading sequence, basically you are, this P1 you are expanding. So P1 is basically composed of chips plus minus 1, and then there is the pulse shaping function. So it is basically plus minus 1 in the form of a pulse. So it is the product of a plus minus 1, which is Pi, and the pulse shaping function, which is the shite chip pulse waveform. So consider a signal xt that is 0 outside the interval 0 to t. So xt, that is time limited between 0 to t. This is basically the matched filter definition. This part is unrelated to this part. This is basically definition of matched filter. So in match filter, basically we design a filter that is a delayed version of the signal, delayed and flipped. So a filter is said to be matched to this signal if the impulse response of the filter is ht equal to x capital T, which is the time period, minus t. So we are flipping the signal minus t, and then we are delaying it. So xt minus t. When xt is applied to a filter matched to it, then the a filter output is given by this function, and the autocorrelation is again given by the autocorrelation definition. And um, finally, yeah, so this is the matched filter response, and it has shown that it is a good for synchronization and for good autocorrelation. So yeah. Wait 1 minute. Yeah. So now we do a matched filter output of a single data symbol. So this is the data symbol. So the data symbol is being spreaded by this waveform. So originally it was a cos theta, basically amplitude into tone, a simple sinusoid. Next we add t1 t minus t naught. So this is the this, what to say, t1 t minus t naught is your spreading waveform. So this is your data signal. Now we have to design a filter that is matched to this. So the matched filter output will be, then you have to do some mathematics basically here, and you just substitute this st is already there. So 2ap, so you put this st as it is, 2ap1 t minus t naught. Yeah. And this p1 ut plus t minus t. So this p1, so you are matching a filter to p1. So p1 is there, you are not matching the filter to the entire thing, you are matching a filter to p1. So p1 ut plus t minus t. So this is your matched filter, and this tone, of course. So you are matching to, yeah, so you are matching, when you are matching this, so t minus t naught becomes capital T minus t, small t becomes capital T minus t. Okay. So finally this is your matched filter part. This is your matched filter. Okay. And you are multiplying the signal with the matched filter. And yeah, then substituting, we will finally get we have to expand this integration, and then we have to, if fc is much greater than the chip type period, then you can finally simplify it to yst equal to ast cos 2 pi fct, where ast is an amplitude function which is inconsequential to the frequency, and basically what it is a single tone. So you get back a single tone function. That is what is important. You get back a single tone function. Yeah, um, that is that. System. Now I will go through some of the MATLAB code. So in these assignments, you might have to generate Walsh-Hadamard code and study its correlation properties. So, so basically the cross correlation and the auto, you have to find the autocorrelation and the cross correlation. So the cross correlation means you take one point and then you take another point of the same sequence but in a delayed domain. So I plus n or I minus L depending on whether L is positive or negative. So one symbol will be taken as it is, which is equal to the running variable of the summation, and another will be taken as the delayed version of that. And that delay basically at every instance of delay. So at 0 delay, 1 delay, 2 delay, you sum these up at all delays and you find the autocorrelation at all delays, and cross correlation at all delays. And then if you take the two sequences to be same, then you get the autocorrelation in the cross correlation. Now the Walsh-Hadamard code is given like this. For 4x4 Walsh-Hadamard is given like this. And how to generate this? So Walsh-Hadamard code, this generation basically there are MATLAB functions. So you don't need to write the equations and solve to solve the Walsh-Hadamard code expressions, and there are ready-made functions. What you can use those, there are no limitation. What you have to do in the assignment is basically you have to find the autocorrelation and cross correlation. So the Walsh-Hadamard code, as you can see, is directly generated using Hadamard. So you just tell what by what. So n cross n, you tell that n. So 4 by 4, 5 by 5, 6 by 6, you tell that 5 by to the MATLAB, and it will generate the Hadamard code of that size. Now, generation of aperiodic cross correlation. So, or aperiodic autocorrelation. So, our autocorrelation cross correlation again is given by the XCOR function. So, if you pass one argument to the XCOR function, it will do autocorrelation. If you pass two arguments, it will do cross correlation. So, again, you pass the autocorrelation or you pass the code that you have generated row by row to get the, because each row is a, here this whole matrix is not a Hadamard code. Each of these rows are Hadamard codes, like plus 1 minus 1 plus 1 plus 1 plus 1 plus 1 minus 1 plus 1, like that. Okay, so each row is a Hadamard code, and here in the H8, the H8, you will see, except for these, if you take column wise this, or if you take row wise, then this row is not a valid Walsh-Hadamard code. But apart from this, all these 7 rows are valid Walsh-Hadamard codes. So you generate the autocorrelation like that for a particular index, say at position 6. So position 6 means See, 1, 2, 3, 4, 5, 6. So this code, you are generating the autocorrelation of this code. You don't have to generate the autocorrelation of the matrix. That doesn't make sense. You have to generate the autocorrelation of each sequence. Each of these is a Walsh-Hadamard codes. Each of these rows, except for the first one. So you generate the cross correlation like that, autocorrelation, and in this you generate the cross correlation. You pass basically two rows of two rows are two different sequences. So you pass the third row and the sixth row of the Hadamard matrix, and you get the cross correlation like that. For like that, you plot for all the delay values, and you will see this is the autocorrelation and this is the cross correlation. You see the cross correlation is limited to plus minus 1, whereas the autocorrelation is strongest at 0, which should be the case. So this is Walsh-Hadamard like that. So similarly, the cross correlation everywhere in any two pairs of code, any two pair rows will always be limited between plus 1 minus 1. It will have three zero values, plus 1 minus 1 0. And autocorrelation will be highest at the shift index 0, and the highest value, that value will be basically the order. So if you take the 8 length Walsh-Hadamard code, the highest autocorrelation value will be 8. Why? Because when you are doing autocorrelation at delay 0, means basically you are doing a dot product of the sequence with itself. So when you do a dot product of the sequence with itself, plus and plus becomes plus, and minus becomes minus, and there is no scope of plus and minus because you are taking the dot product of the same thing. So 1 minute. হ্যাঁ কি হয়েছে? হ্যালো, আচ্ছা, দাঁড়াও দাঁড়াও দাঁড়াও, আমি এখন যাও, এবার বেরোবো, বেরিয়ে আমি খাবো, তারপরে আসবো, আসছি। দরকার নেই, না আমি আসছি। আরে মেঘ ডাকছে, মেঘ অনেক কিছু চুপ করো তো। হ্যাঁ, তো so here you will get this thick as sorry, so 8 length. Why? Because you are dot producting the same thing with itself, so you will always get plus 1 plus 1 plus 1. So you add 8 plus 1, so you get 8. So the autocorrelation will be highest at 8, like that. So yeah, that will be all for this week. Do you have any questions? Next week we will do the mathematics of Galois field. Do you have any question?
No, sir.
Okay, so thank you. You may leave. Um, and the non-coherent system. So next another topic is non-coherent system. So you can see non-coherent system, the wideband filter, this filter, non-coherent system, but we will not go into the details of non-coherent system here. And yeah, I think that will be all for today's class. So this week's coding assignment will involve this week or week 6, any one of those two will involve generating Walsh-Hadamard codes as usual you can generate using the same using the MATLAB inbuilt function. You don't have to write Hadamard codes by yourself. Thank you.